You know, one of the reasons I love coming to skeptical conventions is to hear from the wide breadth of topics skeptics might be interested in. Today we were on not so much the fringes, but it wouldn't be unheard of to hear talks about UFOs and ESP and things like Bigfoot. I've always had an interest in Bigfoot in the sense that it's something skeptics use as a go-to, like, there's no reason there couldn't have been Bigfoot. Gigantopithecus was a thing we see in the historic record. It's plausible, it just seems to happen to not exist, or at least we have no evidence for it. Seems very, very unlikely. So a while ago on Data Skeptic, we tried to do this little experiment. Could we come up with something like the Drake equation? Starting from Gigantopithecus, all of the steps that would be necessary to come up with the probability, however small, that Bigfoot just might be real. And, through that exercise, the number we came up with isn't really important because effectively it's zero. There's such a dearth and absence of evidence in so many ways, but I don't want to call it a zero because I practice something called Bayesian statistics. We never know any certainties, but we can be epsilon close to zero on a lot of these topics. On the flip side of that, there's topics in artificial intelligence that are epsilon close to 1 in their truth. Everyone in here has used Siri and Alexa and things like that. Now, they're not blow-me-away technologies. There's a lot of ways to go, but they're impressive. Self-driving cars are today driving better than human beings by some metrics. Those robots from Boston Dynamics, they're creepy. You should watch the videos of those. They're that real-seeming. I'm surprised there aren't more conspiracy theories that say there's an animal brain inside those. And we'll talk more about AlphaGo a little bit later. The point I'm trying to make is that there's this strong overlap in this Venn diagram about claims people are going to make, related to artificial intelligence and what's scientifically plausible. I love what's in here. I think this area is growing. What's out here is what's interesting to me as a skeptic. So what are people saying about AI? We hear a lot of gloom and doom, not necessarily from everyone. Jeff Bezos from Amazon, pretty progressive about AI. I haven't seemed to find anything in the public statements he's made suggesting he's one of these people that thinks robots are about to take over or anything like that. He invests heavily in the technology, and you can consume the AI services he sells, or the services that are called AI. Musk, on the other hand, pretty bleak outlook in a lot of ways from some of his tweets and public statements. Really thinks there's an existential threat here. Somewhat similarly, Nick Bostrom wrote a great book called Superintelligence, in which he puts forward a lot of ideas about what it will be like if and when we have an artificial general intelligence. And I'm going to use that phrase, artificial general intelligence, to mean the thing we all want to call AI, because the term AI has just been bankrupted by marketing organizations at this point. Hopefully AGI can hold for a while, and that's what I'll mean to say, even if I say AI a bit in this talk. A lot of interesting discussions in the book. I don't agree with everything, but there is one point that might seem non-obvious that I do agree with. He posits that if there were an AGI and we were worried about it, you might think, hey, it's in this laptop. Let's close it off from the outside world. Let's air gap it so it can't get to the internet and things like that, and just talk to it with a certain staff. Could we keep it contained in the box? And while I won't take you through the arguments here, he, like many people, myself included, believe that no, you won't keep that in the box. There are lots of reasons to think that. Some are how it might psychologically convince us to let it out. There are humanitarian reasons that if it truly is an intelligent thing and feels it's imprisoned, who are we to keep it there? You can, formulate your own thoughts about this. But that argument actually convinced Neil deGrasse Tyson to change his mind a little bit on this. And he's now in this camp of people who thinks, yes, we'll let this thing out of the box. So if it's a threat, containment is not the solution. The late great Stephen Hawking was of a similar thought. Physicist, not a computer scientist, not an AI guy, but thinks that AI is really a very real danger to the existential threat to Homo sapiens. Last but not least, one of the best, Ray Kurzweil, who amongst many things that there are to be skeptical of, including his beliefs about extreme long life extensionism, will go so far as to give you dates on exactly when we're going to have these sorts of things take place. And I don't know that he owns them, but there are countdown clocks based on some of his book as to when the singularity will arrive and when we'll all merge with the machines. Perhaps all of these are an appeal to authority. In fact, these are worse than an appeal to an authority. These are an appeal to a pseudo-authority. These were 3 entrepreneurs and 2 physicists, one of which has arguably some good technical chops in the AI world. So let me tell you the perspective of a few individuals that come from the more academic side of AI, names you might not know, but names you should know. Andrew Ng, really well recognized and respected figure in the machine learning community, has this pithy quote I'll share. Worrying about evil AI killing humans is a little bit like worrying about overpopulation on the planet Mars. And read deeply into that analogy. I think it holds up quite well. I had a chance to interview Pedro Domingos about his book, The Master Algorithm, last year. The Master Algorithm is what he calls the ultimate learning algorithm that can do the task that the human brain does today in learning things. We don't have it yet. We maybe have a roadmap for how to get to it, but it's something that is currently sought out by the community, but something that certainly must exist because it exists upstairs here. We just don't know how to make a machine do it. Quoting just a bit of what he told me during the interview when I asked him about some of these topics, the optimization goal is defined by us. And I think that's the key concept here, that when we build AI, we'll build them with some purpose. I'll talk a little bit about that later, but they'll be designed by us. Now, it's very true they may get a mind of their own, but that starting point comes from how we build them. Jeff Hinton, a very important figure in the deep learning research community, and I'm very much quoting him out of context here. When he said my view is to throw it all away and start again, he didn't mean all of AI and all of machine learning and start from scratch. He meant a very specific concept called max pooling. It's something he helped to pioneer. Oh, don't take a picture, it's out of context. Below... This, yeah, all right. This is something called a capsule network. We won't get into it, but basically what he said was this idea of max pooling has been kind of a victim of its own success. It's such a trivially simple approach to doing things. It's worked so well we haven't thought about better ways to do it. And that was part of why he's proposing this idea called the capsule network. Is that the secret to AI? No. Is it one of the pieces? Probably. But continuing down some of these paths, you might think, well, if we build a staircase to get to Mars, we can report a lot of progress along the way. I think that's more along what he meant related to max pooling. Last but not least, here's Stuart Russell, one of the co-authors of the preeminent textbook on artificial intelligence. I searched high and wide to find any sort of gloom and doom quotes he might have, and I couldn't locate any. Most of his comments were relatively positive and couching, skeptical in a way. Although, it should be noted, this paper here that I'm referencing, that he's the lead author on, issues a lot of very serious concerns about what AI can do in the world, and especially in things like military applications. Today's technology, we could put some sort of weapon on a drone with facial recognition technology and send it into a city to locate the right face and drop a bomb on them in a totally autonomous way that doesn't involve a human being. We could do that today. Not very well. I mean, that technology isn't super advanced. Would probably make a lot of errors, but it could be built. Should we be building that sort of thing? That's not a question for the AI people. That's a question for ethicists and politicians, but a question we should be asking. All of this is still a little bit of an appeal to authority, albeit with much better authorities. But perhaps I cherry-pick these people because I like them, or because they share the sentiment I have that AI is not the existential threat it's been made out to be. So let's go to the data. What can we find that's a little bit more conclusive than what a few people have said in comments I chose to pick out? There's a conference called AAAI. It's one of the bigger conferences in artificial intelligence research. In 2016, they asked 192 fellows to take a survey of which this was one question, 80 responses. And to be clear, a fellow, that's some serious stuff. I don't know that I would be allowed to be a fellow. These are accomplished people who know the field. Maybe not every one of them is a brilliant mind. Maybe not every one of them knows everything there is to know about it, but this isn't some Pew poll. They were asked, when will superintelligence arrive? And this is also not necessarily the best question for our forum because superintelligence is perhaps different from intelligence, and we might have to break down what that means, but let's go with it for the moment. 0% thought this would happen in the next 10 years. 7.5 in 10 to 25 years. And where I lie, in the 25 plus category, I have to point out that that's a rather broad area. That includes 250 years and 250,000 years. What's most interesting to me is this 25%. I'd like to talk to those people who say it will never happen. Because one of the things I hope to convince you today is that never is not on the drawing board, unless it's never because we're going to superheat the planet first, or never along those lines. But there's no physical limitation we know of that will tell us that a machine can't think. So 25 years, 250, not quite sure, but certainly not the immediate threat that some of the news media might have you think. The question we're really trying to ask here is, as Alan Turing asked in 1950 in his famous essay on computing and machinery, can a machine think? And what he goes on to do there is to convince us that this is really the wrong question for a number of reasons. First of all, you're going to get mired in definitions of what thinking is. So can we ask a slightly different or more precise question that's equivalent? Instead of can a machine think, we ask, can a machine compete in the imitation game? You may have heard of something called the Turing test, same thing. I'm going to call it the imitation game because calling it that highlights the point that most people miss. I think everybody knows the Turing test is, you put a human judge in a seat in a sealed up room with a computer, and they get to talk to one conversation partner who's a human, one conversation partner who's a machine, and they're asked to distinguish which is which. That's only 80% of the story. The actual Turing test is all about imitation. The human chat participant is asked to behave normally, answer as they would. The machine is designed to pretend to be a human. The machine is actively engaged in deception, and the judge knows it. The judge is asked to try and distinguish between a person who's talking to them normally, a human, and a machine whose objective is to deceive them. Some of you know about tardigrades. They can survive in space. There's certain bacteria that can live on the inside of volcanoes. There's some really cool stuff that extremophiles do. They live very differently than human beings do. They live in places we can't go. And maybe machine intelligence will be of a similar exotic variety. If aliens came here tomorrow against all odds, and when they landed and wanted to talk to us, it turns out they were made of something that looked like pea soup and spaghetti in 2 different jars with a wire connecting it. And they evolved that way somehow. We would test them for intelligence in some manner, and we'd have conversations with them. And we wouldn't say, you don't have a brain that we can clearly tell. You can't be human. You don't think the way we think. If we're not going to prejudice biological intelligence, why would we prejudice machine intelligence? So we might not be able to say it thinks like us or has a brain like us. We need a test that says, can it sufficiently pretend to be us in a way that we can't tell the difference? Turing, in anticipation of what people might say against his arguments, prepared a number of objections. I'll leave this up for a minute without going through too many of them in detail, because I think not all of them really stand up to modern objection. For example, Lady Lovelace's objection that computers do only as they're programmed to do. That made a lot of sense a couple of decades ago, but I don't think anyone in this room would believe that today. The only one that's interesting to me really is the argument from various disabilities, or as I like to say, machines will never. For a while we said, machines will never beat a human being at chess. False. Okay, machines will never beat a human being at Go. False. Machines will never drive a car. False. Machines will never be able to do medical diagnostics and read the images that radiologists read at the same accuracy they can read it. Not only is it false, machines can do it better in some cases. Machines will never create art. False, though arguable, because what is art? Hard to define. Same way as we say, what is it to think? That's why we need the imitation game. These are 2 computers, old ones. Which one of these is better? Everyone would think, oh, the one on the right's better. And depending on what you mean by better, you're right. This one's faster, has more memory, can play games in the way this one doesn't seem to have any games in it. But these computers are the same on some level. If you ask the question, what are they capable of computing? The sets are equal. The one on the right, why don't computers look like that today? It's not because Silicon Valley hates steampunk. It's because this one is cheaper to build and more efficient to build. If you wanted to get a computer like this to do what this one does, it would be 4 football fields big probably and require a fleet of engineers of constant servicing and figuring out what the right material is to make the gears out of, because it's constantly going to fall apart and be broken because it's mechanical, and a lot of headaches that simply don't bear the cost of this relatively easy to build machine in comparison. That's why they look like this. Maybe one day they'll look a little bit more biological if we figure out how to make them that way. Underneath all of these is one simple operation, the NAND operation, or not and. I'm going to walk you through this truth table. This is a circuit, very simple circuit. It takes 2 inputs, A and B. When A and B are both true, we output false. Otherwise, we output true. So not and. If you can make this, You can do anything that a computer can do. You can compute anything that is intuitively computable. Doesn't matter if you have a mechanical computer, a computer somehow made out of water, or the ones we carry around in our pockets today. That's a rather profound statement that might take a degree in computer science to fully appreciate. All I can tell you is that the reason that's true is we scale this up. Any operation you want to do, you take multiples of these and you connect them together in just the right way, and you can compute anything. If you don't believe me, here's how you make a NAND gate in Minecraft. If you don't know what Minecraft is, ask your grandchildren. So there's another old idea. It's the perceptron. This was, I think, the 1960s is where this dates back to. And while it might look ugly, and I know a lot of people don't like to see things with Greek letters in them, because it looks like math and it's scary, I'm going to walk you through it. Just like you have inputs A and B, inputs here we have our x's, and we have more of them. You multiply them by some weight. We don't know what weight. That's what we have to find. And whatever that weight is, you sum them up. So you can imagine if the weight's 0, it's like turning off the input. Anything times 0 is 0. Then you put them through some operation. Doesn't matter too much, but just another mathematical procedure. The kind of procedure that I suspect most 6th graders could do on pen and paper, although a machine does them incredibly fast. When we came up with this, it was sort of the pen and paper days. And no one was able to really take advantage of this for a number of decades. Some people thought it was a dead end. Take this idea on the screen now and picture it as one little circle. Here's a lot of them connected together. This is what's called a neural network, or a deep neural network as we call them today. Same idea, just been rebranded because now it's cool and now it works. Modeled after the brain, although I'm sure a neurologist would shake their head with every analogy I draw of the brain, so I won't go there. But basic idea, yeah, you have your inputs here, some process goes on, the outputs of those passes along further to other layers that do other operations and pass them along, and somehow you go from an input that could be, details about a credit score leading to your FICO score output, or the color values of the pixels of an image, to some output that says whether or not there's a cat in that image. And it's all been about scaling up for the most part. You're all familiar with Moore's law, I'm sure. Every 18 months, we presume that the number of transistors that fit on a chip for a certain fixed cost will double. Moore's law seems to be breaking down a little bit, but that's okay because advancements in computing is showing up in other areas. How we parallelize, maybe if we go in 3D, that's several talks in and of itself. These Pixar movies, they've come a long way in how vivid and amazing the images can look. This is all trigonometry. Just lots of it. It's the geometry you learned in school, figuring out how light bounces off of each other and how shapes move in space and that sort of thing, just scaled up, and now we have the computing power to do it at great scale. So maybe with this sort of technology, if we scale it up just enough, eventually intelligence will be an emergent property out of these machines. Now that's a little bit something to be skeptical of, but I'll give you a maybe on that. Let's talk more about how machines learn. So today anyway, if you give me your height, can I predict your weight? Not perfectly, but I can get to some level of accuracy with it, right? There's a correlation here. The data might look like this. So input is height, output is weight. I want to come up with something called a model. What's the relationship between these two things? Here's two possible models. Which do you guys think is the right one?
The one on the right.
Obviously, right? Why? Well, to you, it might even be hard to say why you think it's right. It just sort of feels intuitively right. Mathematically, we define something called a loss function. We say, what's the difference between the predictions along the red line and the blue dots, our actual data? This one makes a lot of errors. It's off here. It's off on almost all of these. It makes less errors than here. So we find the model that best fits the data we have available anyway. And then this model is described with two parameters. You might remember y equals mx plus b. Your b is the intercept, your m is the slope. This same concept, as you probably know, can be scaled to 3 dimensions easily. Maybe now I get not only your height, but your caloric intake. Still can't perfectly predict your weight. Bone density, metabolism, all these things matter, but I'm getting closer. You gave me a little bit more data, I was able to fit the model a little bit better. And there's a certain magic to this that I can't draw it for you in greater than 3 dimensions, but the math works the same, any number of dimensions. Here's one problem in 784 dimensions. This is a problem a lot of people work on. That number will have given away what this is from to some people in the audience, perhaps. I trust that your sensory inputs don't accept this format very well. So this is the way an exotic computer might want to look at it. Here's a way that's amenable to your input streams. That's a 0. All I did was draw 28 rows of 28 instead of 784 in a row. And instead of 0, I gave you the color white. Instead of 1, I gave you the color black and a gradient in between. Here's another one, and watch how fast you can recognize this one. Instantaneously, it's a 5. But these are two math problems. These are two numbers, not just 0 and 5. They're this vector, each different. And we asked the machine, using the same principles, find a function that maps from this data about pixels to these numbers. And there's a little bit more to it. There are a lot of techniques, convolutional neural networks and layering and things that have to go into this that I won't bring you into, but basically, it's this same problem scaled up. So as we scale it, there are more parameters. The y, the b and the m and the y equals mx plus b equation are just two knobs to fiddle with. When you solve these sorts of problems, there's lots of knobs to fiddle with. And that's a big problem for researchers today, but they're figuring it out. And computers are getting very good at situations where you show them data, you label it, and ask them to learn the relationship. And afterwards, ask them to make new predictions. They've gotten so good at that, we sometimes have trouble explaining how they do it. I'll get back to that later. I first want to tell you about one other way that computers learn besides that labeled approach. What if we didn't want to give them any labels? Much the way humans learn, we just want to send them out into the world and have them learn. We call that reinforcement learning. I promise this is my only equation and I'm not going to go too deeply into it. It's there for those of you that like equations. For those that don't, let me break this down into a simpler form. Imagine if we took that pea soup spaghetti jar alien who doesn't speak English, can't read the instruction manual for operation. We lock them in a room, and we leave the game there with them. No instructions whatsoever. But every time they successfully pull an organ out, we give them 100 points. Every time the buzzer goes off, we give them a shock. Or maybe we feed them and punish them, whatever. To a computer, it's points. You get points for doing good and points for doing bad. And interestingly enough, what a computer will actually do in this situation is sit and do nothing, because that gets you a 0 reward. That's why you tack on this -1 for every second. So it's a little shock every time, which just motivates you to go and figure out how to get a reward. If that sounds a bit Pavlovian, I guess it is, but that's how it works. And if you take this very basic and seemingly simplistic idea, how could that do much more than play video games? Well, it can do a lot more. It can master all the video games in the technology that is also behind something called AlphaGo, that is now the best at playing one of the hardest known games. We don't even know what the next game is to challenge a human and a computer to. We've run out of them. Reinforcement learning is not the only thing at work in AlphaGo. There's a lot of other impressive technologies that made this a possibility, but it's a strong component in it. So, the human brain is billions and billions of neurons. We can't make CPUs with billions and billions of transistors today. But eventually, the engineers are going to figure out how to do that. And at that point, maybe we can simulate the human brain, or maybe we can come up with algorithms that do the same thing more efficiently. Who knows? I'm not a student of history, as you'll soon see, so bear with me. Imagine yourself back in almost prehistory times. The sands of Egypt are here, and one day Pharaoh says, I want a pyramid. And his staff comes and says, Pharaoh, we don't know how to build pyramids. We got a lot of bricks, but there's so many questions. What you're asking for is huge. We don't know how to build the pyramid. Pharaoh got his pyramid. So next step, Pharaoh says, all right, I'm really happy with my pyramid. What can I demand next? I want an Apple store because I need an iPhone. I got to text Cleopatra. I want to read Hammurabi's latest blog and tweet about it. Pharaoh didn't get his iPhone. Why not? Well, there were too many steps, more connections than James Burke could even help us sort through to get from there to here. But could a mogul of today demand the machinery necessary to build an artificial general intelligence? Maybe. A brick is to a pyramid as the neuron is to the brain. And I mean this in the weaknesses you guys all see. The brick alone isn't the pyramid. There's a lot of structural engineering to figure out. How do you even feed your staff? There's a whole economy that had to spring up around that. There's a lot of emergent properties to it. Same thing with the brain. Understanding the neuron doesn't tell us we know everything about the brain. But understanding the transistor also means we may not necessarily know everything about the artificial general intelligence we might one day create. Again, sticking with me being a bad student of history, I imagine at one point civilization started with a couple of little tribes getting together, everybody knew each other's names, and it grew, and it grew and grew, and eventually it was big cities, Tokyo, Manhattan, New York, and things like that. Sorry, that's the same thing. And along the way, a black market emerged. A black market isn't there in the laws of physics, it's not something we had to have, it just emerged. And the witness protection program emerged after that. Isn't that a peculiarity that such a thing would exist? No one really designed it in the sense that the society was designed when you build trains and set up roadways. It just started to come out of the woodwork. And some people believe AI may end up in the same way. There's a lot of discussion in the field right now around something called the interpretability problem. As I mentioned earlier, techniques that exist today can build machines that empirically do amazing things, and we can't fully tell you exactly how they work. Now, there's a lot of efforts to adjust for that or correct for that. Here I'm showing you a visualization of one of those deep learning neural networks. Tons and tons of those perceptrons or something like it, and a lot of different layers and methodologies baked away here to go from the inputs connected to a pixel, just like the digits I showed you, to some label that says it's a cat, it's a face, it's a car, whatever. How does it work? Well, it works by linear algebra. You know, there's a bunch of tensor operations that factor all this stuff out, but that's not satisfying. That's like a physicist telling you why World War II happened by explaining it in terms of superpositions of particles. It might be correct in the sense that those are the laws of nature, and yeah, they explain it, but they're not a satisfying answer. So we try and find some satisfying answers by doing clever things like blocking out parts of the network and seeing how it weakens the ability to predict and saying, oh, this region of the network seems to relate to this. Much the way neurologists today know that regions of the brain seem to relate to things we do, but not perfectly. There's no grandmother neuron we can pull out to delete all your memories of your grandmother. So we're going to have to think more about that Turing test when we evaluate, do we think something's intelligent or not? We're not going to be able to open it up and look under the hood and decide. We can open it up and look under the hood all we want, but this is a complex system. So you may have heard that the Turing test was passed by a chatbot named Eugene Gustman. Eugene Gustman pretended to be a 14-year-old Ukrainian boy with a limited grasp of the English language. So in some sense, you could call that a trick or a hack or why didn't the judge notice it? But actually, you can talk to Eugene Gustman online. This is a transcript from one of my top 3 favorite living computer scientists, Scott Aronson, who went and talked to Eugene. And I think you'll quickly tell, as Scott did, that you're talking to software here. I don't know how someone thought that this was a convincing human chat participant. Maybe they didn't understand the point of the imitation game. I mean, if I ask my phone to set a reminder for me tomorrow, and it does it, we did that in natural language. I don't regard my phone as intelligent for doing that one task. If my phone claims to be intelligent, I'm going to do some tests on it. Those tests will be in the form of the Turing test, but one of the clever things that I might use is something called a Winograd Schema challenge. Take this sentence. The city councilman refused the demonstrators a permit because they feared violence. Okay, same sentence. The city councilman refused the demonstrators a permit because they advocated violence. Who feared and who advocated? It's tricky. You need a lot of domain knowledge to answer that question. You need to know something about city councils and demonstrators, and even sort of socially, we kind of trust that the city council is, I mean, maybe they're a little dirty and corrupt, but it's not like, you know, Al Capone kind of stuff. They were hopefully okay. At least, you know, I'm from Chicago, anyway. These are the kind of things that help us test a machine, maybe, because it have to know the kind of things we pick up in life. It's not knowledge you just program in. The idea that some conversation partner will be the collection of a bunch of phrases a programmer keyed in is just preposterous. It'll be a machine that does certain operations and has some level of understanding of language and context and meaning. Maybe this will have to happen in much the same way that human beings learn. Maybe we'll create software that learns the rest of the way. I hope my siblings never see this. I have some nieces and nephews that I love very much, but honestly, there isn't much to say to them until they're about 5, in my opinion. They're still booting up. And perhaps the same thing will happen when we create AGI. It'll learn a lot of the important steps along the way on its own. And how will we test it? But an empirical test. So, closing in on the end, let's do some lightning round questions. I get asked a lot about transhumanism. You know, are we merging with the machine? What's going on there? Well, this really depends. If one day I go to a doctor and that doctor tells me, Kyle, you need a pacemaker, I'm going to get a pacemaker. And if that pacemaker makes me a cyborg, then sure, I'm a transhumanist. But at the extreme of this, a lot of people talk about uploading the brain. And while I guess in the same way I see no limit on why we couldn't make a machine think, I see no reason why eventually the engineering couldn't get to the point where we could upload a brain in some fashion, although in this context, upload like art and like thinking is a bit strange of a definition perhaps. But this is such distant science fiction, I don't think this is even worth talking about. I had the opportunity to go into the USC Loney lab a while ago and see the profound advancement in imaging they got from going from, I believe, a 5 to an 8 Tesla fMRI, and how much new information was available for them to study, but then yet hear them tell me how far yet they need to look. We can't even fully observe the brain, let alone take any sort of snapshot of it. Quantum, okay. Quantum's a great topic for skeptics. And for the most part, unless you're talking to a physicist, and not all of them, you should be pretty quick to dismiss what most people say about quantum. However, a quantum computer is a very real thing. We're not good at building them today. We think we may have built the most rudimentary versions of them, but if the engineering continues, we'll eventually have one. If and when that happens, you know, there's a bit of an interesting point here that we're talking about a machine we don't yet know how to build. So you might wonder, gosh, what could it do, all these amazing, interesting things we don't know about? That's not the case. We're able to study it in theory. And in fact, a quantum computer is only better than a computer we have today, what I'll call a classical computer, in a number of very specific ways. If we had one today, what would we do with it? Well, there are two major algorithms, Shor's algorithm for search and Grover's algorithm for integer factorization. Those would be much, much faster than a classical computer. But doing integer factorization faster doesn't give you artificial general intelligence. So similarly, the brain doesn't seem to have any quantum phenomenon in it significant to the level that we ascribe our intelligence to it. So while a quantum computer could play some role perhaps, this isn't the key, has very little to do with intelligence as far as I can tell. What about AI and mass unemployment? I mean, this is a tricky one. Quick show of hands, how many of you have anybody in your friend or close social circle who's an out-of-work typewriter repair person? Nobody. Okay. I've never been to a mill town. I've never visited Detroit. I do understand how a radical and quick change in industry can disrupt a social situation, and I have a lot of sympathy for that. But I don't think stopping technology will prevent that, nor do I think technology destroys jobs necessarily. I think it moves them around. And while that might be unfortunate for some people, it is the change that we've been going through for over a century, and AI is not going to eliminate all the jobs, in my opinion. Last but not least, the singularity. So, you know, it's hard to pin down people on what exactly they mean by the singularity, but as best I can tell, it's this belief that technology is going to advance so fast that the machines are, the first generation of AI will write the second generation of AI, and since it's faster than us, it'll produce a faster AI 2.0, which will be 3.0, and off to the races. I don't think so. Here's my main objection to this, and I really draw it out of an excellent conversation I had with computer scientist Lance Fortnow on Data Skeptic last year. He's one of the, in my opinion, world's leading experts in a field called complexity theory, the study of algorithms and how they scale. And I'm taking his idea and applying it in a different way. These aren't his words, but an idea he shared with me when he talked about the friction of difficult problems. There are many problems we know to be difficult. How many of you took an Uber or Lyft here today? Maybe even the Lyft line where you get in with a couple of people. And those companies try and route different passengers to have an efficient way to meet together. They want to get drivers and passengers paired up in such a way that's amenable to everyone in the whole system. That is a provably difficult problem. They're never going to one day crack it overnight. This is always going to be something hard for them to work on. And there are many provable hard problems that exist. That's a property of nature as far as we can tell. So why we would think that some singularity would happen and all the problems would be instantly solved when we know there are hard problems just doesn't make sense to me. So in conclusion, I think AGI might be far off, but it's certainly not impossible. It's close enough we should not necessarily be worrying about an AI uprising. I don't think that's something I could even potentially see in my lifetime. But we should be worried about military applications, not because of the AI, but because humans like to kill each other. So computer scientists love something called recursion. I'll end with a recursive quote. I'm going to quote Russell and Norvig quoting Alan Turing from his original paper, 1950, which, though less true today, still remains true. We can see only a short distance ahead, but we can see that much remains to be done. Thank you.
We definitely have time for some questions.
All right, we have a question right here.
I've been lucky enough to be down at the Googleplex and talk to some of the people who are doing the AI, and they're already at the point where with their TensorFlow processors and things, they've programmed the first generation of AI, and then they've told the AI to go program the next one. And they're getting programming out in the second and third generation, and they look at it and they can't understand what the heck it's doing. So just any comments on what's going on there?
Excellent point, yeah. We're going to have to accept that we now live in a world where we're creating machines we can't fully explain how they work. Imagine, you know, I had drinks with a coworker many years ago. He'd just gone through a divorce, and I said, you know, why'd you guys get a divorce? And he said, you know, we couldn't agree on the length of the towel rod for the new bathroom. And today, I wasn't married then, today I am, and I appreciate how deeply meaningful and profound of a statement that is. Because when you try and explain something, you want this bite-sized, perfect explanation, but complicated things just don't have explanations like that. Intelligence isn't so easy to explain. So we're going to need something other than unpack it and see how it works. We're going to need empirical testing. And in the same way that it took a magician in the laboratory to expose a fraud in the form of ESP, I'm referring, of course, to James Randi and Project Alpha, it may take a magician in the laboratory to expose an AI fraud. We have to think about these things empirically. What is being claimed and what is it said to do? And if the machines write the next generation of machines and they sufficiently solve the problems we ask them to solve, then we'd be grateful that we've done a good job on the engineering problem, I guess.
One of the ways in which science has advanced in terms of understanding the human body and functioning is when we've been able to, in scientific terms, build analogues or discover analogues for processes in the human body. And some really good examples are electricity in terms of the nervous system, the heart as a pump, and so on. And I would suggest that our von Neumann engines with NAND gates, serial processing, digital computing is not an analog for the human brain. And until we finally understand the human brain, we won't be able to build analogs which will give us AGI.
That's certainly a possibility. I can't tell you that you're wrong. I can tell you that my own point of view is that while the human brain is one example of an intelligent machine, I don't think we have to duplicate that machine. Perhaps machine intelligence will be a bit exotic. There is a lot we have yet to learn from the brain. One of the preeminent conferences is called NIPS, Neuro and Information Processing Systems, and over the years, it's really just become a machine learning conference. There's not that much neurology stuff going on there. Apologies to the people who have papers there are, but I think they'd admit they're in the minority. So these fields should perhaps be talking more. I think there's a lot each can learn from one another, but we've had an explosion in advancement in machine learning that hasn't required much input from the neurological world. So while there's certainly likely to be some value there, I don't know that it's required.
Question over here.
Would you comment on Searle's Chinese room?
The Chinese room, sure. The idea that in playing the Turing test, so we have what if instead of a machine in the room, there's a person, and they have a vast library of responses, but they're an English-speaking American who doesn't speak any Chinese. And there's a library of Chinese characters that they don't know how to interpret, but they can image match, write down the comments that come to them from the judge, go look them up in some index, find the right Chinese response, and key that into a keyboard. And they'd be doing a rote process of giving you intelligent responses from the books. So in a weird way, you have an intelligent person being an algorithm to display intelligence in a language they don't speak. Where is the intelligence? Well, I would say that the idea that such a library could exist is really where the breakdown is. The space of all conversations is quite large, and to enumerate every possible response would probably take more space than we could come up with based on the number of protons in the universe, that sort of argument. But if I'm wrong, and if that library could instead fit on a hard drive and just be software, well then suddenly it's come back to the point where it's like the artificial general intelligence. Instead of books, we have a hard drive and a machine that looks up the symbols to the right response. Those responses got there somehow, and we just added a step, basically, is my take on it anyway.
So in a universe that's primarily just noble gases and radiation and very little matter, intelligence or consciousness seems to be an emergent property, at least here on this rock. And I don't understand fully, I mean, obviously no one really understands how it happened, but there are lots of theories. Will there be any parallels, do you think, when AI emerges to consciousness emerging on Earth, whether it was in bacteria's go toward this, go away from this? I mean, will it start that simply?
Really interesting question. It may. Part of what I tried to argue today is that a lot of what we use today in pursuit of AGI are simple techniques scaled up. We could maybe draw a similar analogy that the most basic original life form, whatever it was the most simplest of components that was just barely able to reproduce itself. And then over time, natural selection brought it the diversity we see today. That most basic little fumbly thing, whatever it was, that's kind of like the algorithms I work on. As the techniques advance, we'd be able to draw parallels and learn both ways, maybe even learn something about our own origins, perhaps. It's a very interesting thought. I'm not sure. We've got some questions in the front. Should we take them, or are we doing the mic?
We'll do the microphone.
All right, cool.
Yeah.
When I first learned about AI when I was a student at your institution, it meant artificial insemination. My question is, if you can miniaturize an AGI such that you could inject a thinking entity into the bloodstream to do repairs, how small could you get before you're working in a quantum world where the randomness creates problems for repeatability?
Yeah, that's an interesting idea. It really depends, because those are complex systems at that level, and I know very little about biology, really, but I suspect that if we had some miniaturized, fix a virus type thing, could it go in and extend our immune system, find the virus, rip it in half? When you deal with things that are very small, you're right, it's hard to manufacture them, there's a lot of error involved. To put intelligence at that scale, you have to have computing at that scale. And it's unlikely that you'd miniaturize the minimally sufficient components to be an AI. You'd probably you use a technique like something called a partially observable Markov decision process. And that's a fancy way of saying you describe all the possible situations and you solve it offline, and you come up with what's called a policy. And the policy is like the idiot's guide, like just do as you're told and you will succeed. You can pre-compute that, and if you don't deviate from the policy, you're good. So if something were to be injected in me, I would hope that the battle plan was all mapped out in advance in quite that way. And although the behavior is intelligent, the agent is questionable of intelligence. It's rote. So I think that's the way we would probably go when we get into injecting stuff in the blood.
Question over here.
Hi. Yes, I have a question about that. I heard there's something like 27 million bots on Twitter, and I'm thinking on Twitter or Facebook about teams of AI bots kind of competing against each other. How do you think about that?
Sure. I'm actually very ambitious about what chatbots will be doing in the future. A lot of them we find annoying and trolly today and that sort of thing. Partially that's because the technology to build a a useful and interesting one is not quite there. And also because I don't believe the designers who make them really understand that technology yet. But I fully expect in the next 10 years we'll interact more and more with chatbots, and they will become the new user interface. And it wouldn't surprise me if you and I want to arrange to meet for dinner that we have our chatbots work that out together. That's not an insane claim to make that we're very shortly away from that. That's very practical technology. So in that sense, yeah, chatbots interacting and solving problems together is a very feasible idea as long as we're clear on what problems we think they're solving.
I'm going to focus on something that was really, I think, peripheral in your talk, so it may not be of great interest to you. But I think your analogy or your comment about the typewriter repair person was flip and doesn't really address the problem of employment and the effect of technology on employment. In this country, the number one male occupation is driver, and the number one female occupation is cashier. So we're talking about millions and millions of people. Both of those job categories will be automated too soon to make huge social changes that could absorb that number of employed people. So could you be a little more serious for a moment about employment and artificial intelligence?
Sure, I agree with you that those two occupations are very much at threat, and I hope those people understand that and are now starting to take the actions required to make that transition. There's still time. Technology is disruptive, and it does hurt some people. I don't see an alternative to that, though. Do we outlaw self-driving cars? Do we outlaw faster internet connections? But I do think that the economy will evolve. It's not that we'll have mass unemployment. Those people will find employment, maybe after a very painful search, maybe after an expensive, difficult retraining period, but opportunities will arise. Somebody's going to make a lot of money when those two things operate, and they're going to spend that money on something, and that's going to require a labor force to act out whatever they're trying to spend it on. So I think new jobs will emerge. Maybe not as quickly as would be most beneficial for society. Maybe we should have all these discussions about training programs and whatnot, but I don't think mass unemployment is a real concern with regard to the dynamics of economy.
Okay, that's the last question for Kyle, but he will probably be around if you have other questions for him. We will be back for the next talk at 3:05. Thanks.